For chapter 19, actually chapter 18 and 19, is Kirchhoff rules. Kirchhoff has two rules, a junction rule and a loop rule. We actually kind of hinted at both of these rules when analyzing other circuits that we completed, but now we're going to formalize this a little bit more. After we get done with this, the rules and an example problem, you have a graded homework assignment that you need to turn in, and then we'll be done with chapter 18 and 19, and we'll continue on to the next topic, AP Physics 1. So, Kirchhoff junction rule has to do with currents. So, at any junction or point, sometimes websites or physicists call them nodes, and we'll take a look at those just a little bit. The sum of all currents entering the junction or point must equal all currents leaving the junction or point. All currents going in must equal all currents going out. You can think of it as a water hose. It's water flowing through a pipe or water flowing through a hose. If you have one hose, and then you have two hoses connected to the end of that, all the water through the main hose has to flow through the two other hoses. So all the water going in must equal all the water going out. We'll take a little diagram and see how that works. So we have a circuit here with a battery. We'll connect this circuit to two resistors in parallel. And we'll connect those to, let's put a resistor here in that circuit. All right, now let's take a look. We know the direction that the current should flow in the circuit. There's current coming from the battery. This is the positive terminal of the battery, this is the negative terminal, and the current always flows from high potential to low potential, so the current is going counterclockwise around the circuit. So you can think of this as a water pipe coming, and the water going through here. This is some device, like a little water wheel or something that is used here, but all this water flows through this water pipe here. We're going to call this current 1. This current meets this point, our junction, our node. At that point right there, you can think of this as two pipes or water hoses connected to one water hose. Some of the water will go here, some of the water will go here. So when the current hits here, some of the current will go up here. I'm going to call this current 2, and some of the current will flow through here, current 3. How much current flows through here and here depends on the resistors or the device that's in that circuit. So all the current in here must equal all the current going out. When we reach this node, all the current going in, I2 and I3, must add up to be I1. All of this bottom branch of this circuit is one current. This is I1, this is I1. All of this is the same path. Since all this is the same path, it all has the same current. So all the current going in at that point is I1, must equal all the current going out, which is equal to the sum of I2 plus I3. Let's see how we can write this to a little different circuit, and it works the same way. So we're going to have, so this goes for this. At this point right here, you have to identify the point which you're talking about. We're going to come look at another point here in a little bit. Let's have another circuit. Let's say we have a battery this way. We have two resistors in parallel, like this. Again, the current is going to flow in this direction now, because it always goes from high potential to low potential. We're going to call this current 1. And at this point right there, that current breaks up into two currents. We'll call this one I2, and this current I3. Again, we're going to pick any point. When we use this point, or node, or junction, all the current going into that point, which is I1, must equal all the currents going out, which is I2 plus I3. Again, it doesn't matter. Again, this is this point right there. This is actually this point. I could have picked this point over here. All the currents going in at this point is I3 plus I2, because there are two currents going into that point, and this is all I1 must equal I1. Notice those two equations are the same thing. This is at that point though. If we analyze this junction right here, currents going in are I2 and I3, that must equal all the currents going out, which is I1. Again, these two equations are actually the same equation. Doesn't matter which point you pick, but you must pick a point where all the currents are going in or out of that point. So that's Kirchhoff's junction or point rule. Let's take a look at Kirchhoff's loop rule. It has to do with voltages or potential difference. The sum of the changes in potential around any closed path of a circuit must equal 0. It's like if you start at the top of a table and you move your hand from the top of the table to the chair, you've gone through a potential difference. And you move your hand from the chair to the floor, you've gone through a potential difference, and if you move your hand from the floor to back to the top of the table, you've gone through another potential difference. But that entire potential change, if you start at the table and move your hand anywhere and end up back at the table, the total potential change is 0. Same thing with currents flowing through the circuit. If you start at one point in the circuit and end up at the same point, the total potential change is 0. Let's see how that works. Let's make a circuit. This is the battery. Let's say this is a 12-volt battery. We have one resistor, and we have another resistor. Let's say this is a 400 ohm resistor, and let's say this one is a 290 ohm resistor. We're going to call this point A, this is point B, this is point C, say this is point D. And the current is going from high to low potential. Now, because this is a series circuit, all the current flowing through that circuit is the same. So we can figure out the total current going through there. We have to figure out the equivalent resistance, which is simply the sum of those resistors, which is 400 ohms plus 290 ohms. So we get this equivalent resistance to be 690 ohms. To figure out the current, take the voltage, which is the current, times the equivalent resistance. The voltage is 12 volts. Current times 690 ohms. We get this current to be 0.0174 amps. Right. Now let's take a look at the potential difference. Let's go from A to B. From point A to B. We're going to go from A to B, B to C, C to D, and back to A again. So let's take a look. So we want, go from A to B, we want the potential difference between A and B, which is simply equal to the current times this resistor. The current going through here times that resistance, that's the potential drop. And since current always flows from high potential to low potential, that is a potential drop. Current always flows from high to low. Same thing with this resistor. This is the positive, this is the negative side of the resistor. Current always flows from high to low resistance. So this is actually going to be a potential drop. We'll call that negative. The current is 0.0174 amps times our resistance of 400 ohms. We get negative 6.96 volts. That's from A to B. Now let's go from B to C. This is the potential drop from B to C. Again, it's IR, but it's a potential drop, so it's going to be negative, which is going to be 0.0174 amps. The current is the same through both resistors. The current is the same through this resistor as this resistor. But again, we go from B to A, which is a potential drop, that's why it's negative, times that resistance, which is 290 ohms, and we get negative 5.05 volts. Now we're going to go from point C to point D, C to D. We're going across a battery this time, and going from C to D, this is the negative terminal of the battery, this is the positive terminal of the battery. We're actually going from low to high potential here. So the voltage drop from C to D is actually a positive 12 volts. It's actually an increase in voltage because the battery works to push that electron back from low to high potential so we can keep having the current flow through that circuit. Now let's go from D to A. From D to A, potential from D to A, there's no potential drop there. That's all one path. There's no battery in that path. There's no resistor in that path. So that potential drop is simply 0. So then if we add all these voltage drops together, the total voltage from A back to A, we're going from A to A, this is an A, this is an A. We add all these up, negative 6.96 volts, plus negative 5.05 volts, plus 12 volts. We virtually get 0 volts, taking into account some minor error. So there's no potential change if you start at the same point in the circuit and move through a closed path to that same point. So Kirchhoff's loop rule is simply this. The sum of all voltages around a closed path is 0. Now I know that's redundant because it's the same thing that's set up there, but it's important to remember. So the loop rule Because all the voltages in a closed loop adds up to be 0. In the point rule, all the currents going into a point, all the currents going into a point must equal all the currents going out point. Sum of all currents going in equals sum of all currents going out. We're going to use those two rules to solve a more complex circuit. So let's take a look at this. Here we have a circuit. Looks like a circuit we have done before, but it's a little different. This is actually EMF 2. This is EMF 1, right? Notice we have multiple resistors in series and parallel, but notice this one we have 2 batteries. Now, what type of device would have 2 different batteries? Why would you need 2 batteries in one device? Well, you have something that has 2 batteries in it, probably something that's sitting beside you right now. That's a calculator. Your calculator has 2 power sources in it, actually. You open up the back of your calculator. This is one set of batteries, one set of power source. If you open this up, there is a rechargeable battery right there. That way, if you take these batteries out, this battery right here keeps all the stuff in the memory of your battery there. If this battery wasn't available, you would lose everything you put in your battery to begin with. So this is a power source, and this is the power source. So this is a device that has 2 batteries or 2 power sources that keep it going. And there are other things also. Let's take a look how we can do this. But now, because we have 2 batteries in there, we just can't combine those resistances because we can't eliminate that battery. So we have to do this a different way, a little more interesting way to solve this problem. So the process of solving this type of circuit with multiple power sources in it is we have to label all the currents, write Kirchhoff's point rule, write Kirchhoff's loop rule, and then solve for the unknowns. What we want to do here, we want to solve for all 3 currents in this circuit because there are 3 different currents. Let's take a look. Let's say this top branch will have a current going through it, this middle branch will have a current going through it, and this bottom branch will have a current going through it. Now we're going to draw the currents this way. Now you don't know for sure which way the currents are going, but you know there are 3 different ones. I'm going to call this one current 1. I'm going to call this one going down this bottom branch current 2. I'm going to say current 3 is going this way through that middle branch. We have 3 different currents in that circuit, so we need to draw those currents and label them appropriately. We have 3 different parts of the circuit, we have to have 3 different circuits. And then what we do, we start writing, we labeled all the currents, write Kirchhoff's point rule, the next thing. So we have a point rule. The point rule, we pick one point where all the currents go into or out of that point. And I'm going to use this point right there. You should identify which point on the circuit you're using. Point right there, you can put a P there if you want to, that point is what we're using. We could have also used this point, it doesn't matter. We could have used either one, they will both work. But we need to pick one, I'm going to pick that point right there. So then, all the currents going into that point, there's only one current going in, that's I3. So I'm going to write I3. Must equal the sum of all the currents going out of that point. I1's going out and I2's going out. So I'm going to put I1 plus I2. Now, in order to solve this, I'll show you why we're doing this later on, but what we want to do, we can put all the currents on one side of the equation. So I'm going to put I3 all the way to the other side. So we have all the unknowns on one side. So if I subtract I3 from this side, I'm going to get 0 equals I1 plus I2 minus I3. Okay? That's a point rule. Now we write Kirchhoff's loop rule. We need to write enough loop rules to take into account every branch of the circuit at least once, right? So what I'm going to do, I'm going to use the top branch and the bottom branch. Now we could have used the top branch and the entire outside, or we could use the bottom branch and the entire outside, but we just have to have enough loop rules to cover at least every branch of the circuit one time. So we do loop rules. And remember, in a loop rule, wherever you start and end up, you start and end up at the same place, the total voltages add up to be 0. I'm going to start right here with the top loop, okay? I'm going to do the top loop first. I'll put up here, top loop, so I don't forget which one I use, the top loop. I'm going to start here. Now when a current goes through a resistor, it always goes through a resistor from high potential to low potential. So if current is going this way, like water flowing down a river or over a dam, it always goes from the high potential or the top potential side to a low potential side, high to low. I'm going to label this. This is the high potential positive, this is the negative. So if it goes from high to low, that voltage is dropping. Okay? And remember, we have Ohm's law. And I'm going to write Ohm's law this way. V is equal to R times the current. It doesn't matter if I take RI or IR, it's resistance times current, R current times resistance. I'm going to write it this way so we can see how this works. So I'm going to start at this point, go all the way on, end at this point, and all those voltages, when I start in, must add up to be 0. So the total voltage is going to add up to be 0. That's the result that we're going to get. The voltage drop here is going to be this resistance, 30 ohms, times I1, but it's a voltage drop, so it's going to be negative 30 I1. Again, 30, I'm going to leave the units off, make it a little easier to analyze this. 30 ohms is the resistance, I1 is the current, this is a voltage drop, going from positive to negative. Then we go to the next device, we're going through this top loop, so I'm going from this battery, negative terminal to positive. Again, this is negative, this is positive. So we're actually increasing in voltage there. So this is going to be plus 45 volts. I hit this internal resistance, we just treat it like a regular resistance. The current, this is I3, that's going through this. It always goes from high potential to low potential. So this is the potential drop. So it's going to be minus the resistance, 1.0 times the current, which is I3. And I hit this resistor. Again, this is the positive end of the resistor. This is the negative. Always go from high to low. Current always goes from high to low. So this is going to be 40 ohms times I3, but it's the drop, so it's going to be negative 40 ohms I3. Leave the units off, make it a little easier to analyze this. Okay? So now, I'm going to come back to this just a little bit, so leave a space below here. Now I'm going to do the bottom loop. Because I need to take into account every branch of the circuit. I haven't taken into account this bottom branch yet. So I have to use a loop that takes into account that bottom branch. I'm going to use this bottom loop starting from here and going around that way. All right. So I'm going to start here. And I'm going to go around this bottom loop. Notice now I'm going physically moving from the negative to the positive side of that resistor. That's as if you jumped off a diving board. Well, here you jumped off a diving board going from positive to negative, so you lost potential. Here you're climbing back up the stairs to the diving board. You're getting back up to a higher potential. So if you go physically move from negative to positive, that's a potential increase. So this is going to be 0. We're going to start here. And end there. So the total sum is going to be 0, we know that. So this is going to be a positive 40 I3. Then I hit this resistor, again, we're going negative positive, so this is going to be a positive 1. Sorry, that's a 1. It's a 1 I3. Let me erase that a little cleaner there. 1 I3, or you can just put I3, that's the same thing. And then we're going from the positive to the negative terminal of the battery. Again, that's positive negative, so we're decreasing voltage, that's going to be negative 45 volts. And we come down here. This is all I2. All of this is I2. I2 goes this way. So this is the positive terminal resistor, that's the negative. So we're going, again, increasing voltage, so it's going to be a positive 20 I2. Again, all this bottom branch is I2. So we get it here again. Since I2 is going this way, this is the positive part of the side of the resistor, this is the negative, so we're going plus 1.0 I2. Then we hit this battery, this is the positive terminal battery, this is negative, so now we're decreasing the voltage going across that battery. It's going to be minus 80 volts. Then we come back to where we started, we're at 0. So all those voltages have to add up to be 0. Now let's take a look. I'm going to come back up to here. I'm going to rewrite this. I want all of my unknowns on one side, so all the resistance times current on one side, and all the known voltages on the other side. So I'm going to write this. Notice there's a 45 volt potential. I'm going to move that to the other side of the equation, so that's going to be negative 45 volts. And then I'm going to combine any common currents. I only have one I1, so that's going to be a negative 30 I1. Notice there are no I2, so I'm going to put plus 0 I2. If there are no magnitudes of that current, I'm going to still put 0.0 plus 0 I2 just so it gives me a coefficient in front of that number in order to solve this problem better. Then let's look at the I3s. Here's an I3 and there's an I3. We're going to combine the I3s, so that's going to be minus 41 I3. So here is our complete loop equation with voltages on the left side, known voltages on the left side, and all the currents on the right side, all the unknowns, that aren't currently actually voltages, but all the unknown voltages on the right side with the unknown variables. Do the same thing for the bottom loop. We're going to combine our voltage, there's negative 45 and negative 80, that's negative 125. Move it to the other side of the equation, becomes positive 125 volts. There are no I1s, so I'm going to write 0 I1. Look at all the I2s. There's an I2, there's an I2, combine that. That's going to be 21 I2, so we got plus 21. I2, look at I3s. There's an I3 and there's an I3, combine those, it will be plus 41 I3. So now, we have how many unknowns? We have 3 unknowns. We have I1, I2, and I3 for unknowns. In order to solve 3 unknowns, you have to have 3 equations. Well, look what we have. There's 1 equation, there's 2 equations, and there's 3 equations. Now, how do you solve 3 unknowns with 3 equations? Well, you can do it the easy way with your calculator. So we're going to do, all of you should have a graphing calculator, and you should all have polysimult in it. If you don't, it'd be wise for you to get polysimult. Let's go through and see how this works. Turn the calculator and clear everything. So what we're going to do, we have 3 equations. So we go to the apps menu and find polysimult 2. Polysimult 2. And hit enter that advertising screen. And we want to go to the second one, number 2, simultaneous equation solver. 2. Number equation is going to be 3. Number unknowns 3. We'll hit this next, this button right here. Let me see if I can show that a little better. There's a button right here below that. Next, we hit that button. Go to the next one. And this is our matrix. We have a 3 by 3 matrix. This column is for I1, this column for I2, this column is for I3. These are the voltages, okay? So let's take a look at this first equation. This is our first equation. This is coefficients for I1, coefficients for I2, coefficients for I3, and the voltages. So in our first equation, the coefficient I1 is 1. Enter. The coefficient for I2 is 1. Enter. And then this is for coefficient for I3 is negative 1. We should put a negative 1 in there. Enter. And the voltage, or the constant, is 0. That's 0. Now we go to our second equation. This is the second equation. This is the coefficient in front of I1, which is negative 30. Enter. Coefficient for I2 is 0. Coefficient for I3 is negative 41. And the constant, in this case, the voltage, is negative 45. Enter. The same thing for the third equation. The coefficient in front of I1 is 0. Coefficient in front of I2 is 21. Coefficient I3 is 41. And the constant, which is voltage, is 125. Enter all those values in, and you hit solve. X1, X2, and X3 are our currents. This is current 1, current 2, and current 3. So the values, I1 is equal to negative 0.858 amps. I2 is equal to 2.58 amps. And I3 is equal to 1.73 amps. We rounded to 3 significant digits. Now the reason this is negative is simply because, let's look at I1. The reason this is negative is because we happen to choose the wrong direction for I1. I1 is not actually going in this direction, it's actually going in the counterclockwise direction, but don't change it. This means that we simply guessed wrong. It doesn't matter which way you guess the current to be. When you do the calculations, it'll tell you whether you guessed correctly or not. It's not wrong, it just means, well, the current should have been going this way, but it doesn't matter because you have that indicated in your answer. Okay? That's it for chapter 19. Take a look on the LMS for your homework assignment. There'll be, I think, 3 graded homework assignments that you have to do, all of them involving Kirchhoff's point and loop rule.